Hi everyone, I'm Lap-Loi Chung from the National Center for Research on Earthquake Engineering and from the Departments of Civil Engineering, National Taiwan University and National Cheng Kung University. This is my name in Chinese, Zhong Li Lai. Welcome to the course Introduction to Seismic Design of Structures. This is Lecture 7. Seismic Analysis of Single Degree of Freedom Structure. Single degree of freedom structure is a structure which displacement can be specified by only one single variable. And seismic analysis is to analyze the structure under earthquake. And here are some terminology. Base excitation. Instead of applying the force directly on the structure, the base of the structure is excited, is driven, and is called base excitation. In Chinese, 基底震动. Ground acceleration is the acceleration of the ground. In Chinese, 地表加速度. Seismic response is the response of the structure under earthquake. In Chinese, 地震反应. Structural relative displacement. In Chinese, 结构相对位移. Under earthquake, the response of the structure, we are interested in relative displacement instead of absolute displacement because relative displacement is related to the safety of the structure. And relative displacement is the displacement relative to the ground. Structural relative velocity is the velocity of the structure relative to the ground. In Chinese, 结构相对速度. Structural absolute acceleration is the absolute acceleration of the structure. In Chinese, 结构绝对加速度. And we are interested in absolute acceleration rather than relative acceleration because absolute acceleration is related to inertial force. And inertial force of the structure is the seismic force applied to the structure. And a single degree of freedom, from the previous lecture, a single degree of freedom can be modeled as mass, spring, and dashpot system. And Ft is the external force applied to the structure. And from the force equilibrium, including inertial force, damping force, restoring force, and external force, the equation of motion of the structure can be described as second order non-homogeneous differential equation with constant coefficient m, c, and k. And m is the mass of the structure, c is the damping coefficient of the structure, and k is the stiffness of the structure. And if the data of external force is taken every sampling period delta t, after sampling, we have the information about the external force only at 0 delta t, 1 delta t, 2 delta t, etc. Other than that, we have no other information about external force. If delta t is small enough, then we can assume that Ft is constant between two consecutive sampling instants, n delta t and n plus 1 delta t. Therefore, between two consecutive instants, Ft equal to Fn delta t is a constant for t larger than or equal to n delta t and less than n plus 1 delta t. Under this assumption, the differential equation can be reduced to first-order difference equation. Therefore, from the information at current step, including displacement at step n, velocity at step n, and external force at step n, then we can compute the displacement of the structure at next step, n plus 1. And this is first-order difference equation. The coefficient A11, A12, and B1 are constants. they are function of damping ratio zeta, natural frequency omega 0, sampling period delta t, and damp natural frequency omega d, and also the stiffness of the structure K. Therefore, K A11, A12, and B1 are constants. They are not function of T. They will not vary with time T. Therefore, the displacement can be calculated step by step. Similarly, we have the first order difference equation for velocity. From the information at current step n, including displacement xn, velocity x dot n, and external force Fn, we can compute the velocity of the structure at next step n plus 1. Therefore, x dot at n plus 1 equal to A21 times x of n plus A22 times x dot of n plus B2 times Fn. A21, A22, B2 are functions of natural frequency omega 0, damp natural frequency omega d, damping ratio zeta, sampling period delta t, and the mass of the structure m. Therefore, A1, A21, A22, B2 are all constants. They will not vary with time. Therefore, from the information at current step n, we can have the velocity at next step n plus 1. If we repeat this process step by step, we can have the velocity at every step so that we can complete the seismic analysis of the single degree of freedom structure. From the force equilibrium equation, we can have mx double dot plus cx dot plus kx equal to ft. If we divide the whole equation by m, so that we have x double dot equal to minus k divided by m times x, minus c divided by m times x dot, plus 1 divided by m times f. If we assign t equal to n plus 1 delta t, then we can compute the acceleration with this equation. X double dot at n plus 1 minus k divided by m times x at n plus 1 minus c divided by m times x dot at n plus 1 plus 1 divided by m times f at n plus 1. Therefore, from the information at step n plus 1, including displacement, velocity, and external force, then we can compute the acceleration at step n plus 1. Now, if the external force is replaced by basic excitation, therefore, instead of applying the force directly on the structure, we excite the base of the structure. Then it's called base excitation of the structure. If the base excitation is induced by earthquake, and from the seismic analysis of the single degree of freedom structure, we can have the seismic responses of the structure. And here's the free body diagram. And from the Newton's second law, Ma is the inertial force equal to the resultant force. And A here is we have to remind that A is an absolute acceleration of the structure. Therefore, A equal to x double dot plus x0 double dot. Because x double dot here is the relative acceleration, and x0 double dot here is the ground acceleration. Therefore, the absolute acceleration equal to the relative acceleration plus the ground acceleration. And if we have displacement to the right with xt, then we have the restoring force equal to minus kx. If we have the velocity to the right x star, then we have the damping force cx star. And if we move minus kx to the left-hand side of the equation, minus cx dot to the left-hand side of the equation, and A is the combination of relative velocity, relative acceleration x double dot, and ground acceleration x0 double dot. And if we move m times x0 double dot to the right-hand side of the equation, then we have the second-order differential equation of the structure. Mx double dot plus Cx dot plus Kx equal to minus m times x0 double dot. And here's the equation of motion under ground acceleration. We have mx double dot plus Cx dot plus Kx equal to minus mx0 double dot. And with two initial conditions, initial displacement equal to 0, initial velocity equal to 0. Compared with the information we discussed last lecture, and the external force Ft is replaced by minus mx0 double dot. And the motion equation can be considered as force equilibrium equation, including initial force m times x double dot plus x0 double dot, damping force Cx dot, restoring force Kx, and ground acceleration x0 double dot. And m is the mass of the structure, c is the damping coefficient of the structure, k is the stiffness of the structure. And I have to remind that x is the relative displacement, the displacement of the structure relative to the ground. X dot is the relative velocity, is the velocity of the structure relative to the ground. And x double dot is relative acceleration, is the acceleration of the structure relative to the ground. And x0 double dot is the ground acceleration. And it's a second order, non-homogeneous, because of the non-zero forcing function. Ordinary differential equation with constant coefficient m, c, and k. They do not vary with time. If the ground acceleration is taken at every sample period delta t, therefore we have the information about ground acceleration at 0 delta t, 1 delta t, 2 delta t, etc. Other than that, we have no information about the ground acceleration. And if the sample period is short enough, then we can assume that the ground acceleration is constant between two consecutive sampling instants, n delta t and n plus 1 delta t. Therefore, x0 double dot t equal to x0 double dot n delta t, when t is larger than or equal to n plus n times delta t and less than n plus 1 delta t. And under this assumption, we can reduce the differential equation into difference equation. Therefore, we have x at n plus 1 equal to a11 times x at n plus a12 times x dot at n plus b1 bar x0 double dot at n. In the previous lecture, the first forcing function is ft, but in this lecture, ft is replaced by minus mx0 double dot. If the forcing function is ft, then we have the coefficient b1. But now, ft is replaced by minus mx0 double dot. Therefore, we have the coefficient b1 bar. And b1 bar equal to minus m times b1 equal to something like that. And a11, a12 are the same as the previous lecture. Therefore, from the first order difference equation, we can compute the displacement, the relative displacement at step n plus 1 from the information at current step n, including the displacement, relative displacement the velocity, relative velocity, and the ground acceleration x0 double dot. And similarly, we can have the first order difference equation for relative velocity, the velocity of the structure relative to the ground. Therefore, from the information at current step n, including relative displacement x at step n, relative velocity x dot at step n, and ground acceleration x0 double dot at step n, we can compute the relative velocity x dot at step n plus 1. Originally, if the forcing function is ft, we have the coefficient b2, but right now, ft is replaced by minus mx0 double dot. Therefore, b2 is replaced by b2 bar, and b2 bar equal to minus m times b2 equal to something like that. A22, A21, and B2 bar are functions of natural frequency omega 0, damp natural frequency omega d, damping ratio zeta, sampling period delta t. Therefore, these coefficients are constant. They do not vary with time. Now we consider the force equilibrium equation mx double dot plus cx dot plus kx equal to minus mx0 double dot. If we move minus mx0 double dot to the left-hand side of the equation, then we can have m times x double dot plus x0 double dot. And x double dot is the acceleration of the structure relative to the ground, and x0 double dot is the ground acceleration. Therefore, the addition of these two becomes the absolute acceleration of the structure. And if we move cx dot to the right-hand side of the equation, it becomes minus cx dot. Kx to the right-hand side of the equation, it becomes minus kx. Therefore, we have xa double dot. A here stands for absolute. Therefore, xa double dot equal to the absolute acceleration of the structure, equal to x double dot plus x0 double dot, equal to minus k divided by m times x, minus c divided by m times x dot. If we assign t equal to n plus 1 delta t, then we can compute the absolute acceleration at step n plus 1. Therefore, from the information at step n plus 1, including this relative displacement and relative velocity, then we can compute the absolute acceleration at n plus 1. Therefore, xa double dot at step n plus 1 equal to minus omega 0 squared times x, the relative displacement, at n plus 1, minus 2 zeta omega 0 times x dot, the relative velocity, at n plus 1. Therefore, we have three equations. One equation for the displacement is a difference equation. One equation for the relative velocity is a first-order difference equation. Another equation for the absolute acceleration. When n equal to 0, x0 double dot is given. The ground acceleration at step 0 is given, and x0 equal to 0 is given by the initial displacement. X dot of 0 equal to 0 is given by the initial velocity. And from the third equation, we have the absolute acceleration xa double dot at step 0 equal to minus omega 0 squared times the relative displacement at step 0 minus 2 zeta times omega 0 times the relative displacement, the relative velocity x dot of 0. Because of 0 initial conditions, x0 equal to 0, x dot of 0 equal to 0. Therefore, we have xa double dot of 0 equal to 0. So far, we have complete all the information at step 0. Then we move to step 1, n equal to 1. When n equal to 1, the ground acceleration is already given. Therefore, we have x0 double dot at step 1. And from the first equation, it's a first order difference equation. Then we can compute the displacement at step 1 equal to A11 times the relative displacement x at step 0 plus A12 times the relative velocity at step 0 plus B1 bar times the ground acceleration at step 0. The information at step 0 has been given or calculated so that we can compute the relative displacement at step 1. Then from the second equation is a first order difference equation. From the information at step 0, including the relative displacement, the relative velocity, and the ground acceleration, then we can compute the relative velocity of the structure at step 1. Then from the third equation, we can compute the absolute acceleration at step 1 equal to minus omega 0 squared x of 1 minus 2 zeta omega 0 times x dot of 1. After finishing this step, we have all the information of the displacement, velocity, and absolute acceleration at step 1. Then we move to step 2, n equal to 2. When n equal to 2, the ground acceleration is already given, so that we have x0 double dot 2. And from the first equation, the first order difference equation for relative displacement, from the information at step 1, including the relative displacement x, the relative velocity x dot of 1, the ground acceleration x0 double dot of 1, then we can compute the relative displacement of the structure at step 2. And from the second equation, once we have the information at step 1 from the previous step, including the displacement x of 1, the velocity, the relative velocity x dot of 1, the ground acceleration x0 double dot of 1, then we can compute the displacement, the relative velocity at step 2. And from the third equation, once we have the information of displacement at current step 2, the information of the relative velocity at step 2, then we can compute the absolute acceleration at step 2. Once we finish this step, we have the relative displacement at step 2, the relative velocity at step 2, the absolute acceleration at step 2. If we repeat this process step by step, then we can have the relative displacement, relative velocity, and absolute acceleration of all steps. Therefore, we can complete the seismic analysis of the structure. And here's an example about the base excitation of the single degree of freedom structure. And the mass of the structure M equal to 2,000 tons. The stiffness of the structure K equal to M times 2 pi square equal to 78957 kilonewton per meter. The damping coefficient equals to C equal to 0.1 times square root of MK equal to 1256.6 kilonewton per meter per second. From K, the stiffness of the structure, M, the mass of the structure, we can compute the natural frequency of the structure, omega 0, equal to 2 pi, equal to 6.283 radian per second. If we divide omega 0 by 2 pi, we can have F0 equal to 1 Hertz. That's 1 cycle per second. From the reciprocal of F0, we can compute the natural period of the structure T0 equal to 1 second. From the damping coefficient C, the mass of the structure M, the stiffness of the structure K, we can compute the damping ratio zeta equal to 0.05 equal to 5%. From the natural frequency omega 0 and damping ratio zeta, we can compute the damped natural frequency omega d equal to 6.275 radian per second. From omega d divided by 2 pi, we can have the damped natural frequency Fd equal to 0.9987 Hertz. It's very close to 1. It's 0.9987 cycles per second. From the damped natural frequency, we take the reciprocal of Fd, we can have the damped natural period Td equal to 1.0013 seconds. It's very close to 1 second. The initial conditions are given. Initial displacement x of 0 equal to x0 equal to 0. The initial velocity x dot of 0 equal to x0 dot equal to 0. And the sampling period of the ground acceleration equal to 0.004 seconds. From the damping ratio zeta, natural frequency omega 0, sampling period delta t, damped natural frequency omega d, we can compute A11, A12, A22, A21. And A11 is non-dimensional, no unit. A12, the unit is second, s. A21, the unit is 1 divided by s. And A22 is non-dimensional, no unit. We can also compute the B1 bar and B2 bar from the natural frequency omega 0, damping ratio zeta, damped natural frequency omega d, sampling period delta t. We can compute B1 bar and B2 bar, something like that. The unit for B1 bar is second square, and the unit for B2 bar is second. And here is the ground acceleration. Is taken by the station, monitoring station TAP-097 from the Central Weather Bureau. And this is the ground acceleration in east-west direction. And from the plot of the ground acceleration, it can be found that the peak ground acceleration PGA equal to 96.24 Gale, and 1 Gale equal to 1 centimeter per second square. And if we repeat the process step by step, we can have the relative displacement of the structure. This is the displacement of the structure relative to the ground here. And the relative velocity, the velocity of the structure relative to the ground is plotted here. And the peak and the absolute acceleration of the structure is plotted here. And first you have to check the initial values. Are they reasonable or not? If we go back to the previous line, this is the ground acceleration of the excited to the structure. And there's no acceleration, almost no acceleration for the first 20 seconds. Therefore, no relative displacement for the first 20 seconds, no relative velocity for the first 20 seconds, no absolute acceleration for the first 20 seconds. It's reasonable. Then check the vibration period. Is it close to the damped natural period? Almost 1 second. Therefore, you have to check the vibration period. Is it close to 1 second? If so, then it's reasonable. And then check the peak values. We have the peak structural relative displacement equal to 5.637 centimeter, x maximum. Then we have the peak structural relative velocity, x maximum equal to 35.05 centimeter per second. And also we have the peak structural absolute acceleration from the plot here, x double dot A maximum equal to 223.6 scale and 1 scale equal to 1 centimeter per second square. And here we have the peak relative displacement equal to something like that, the peak relative velocity something like that, and the peak absolute acceleration something like that, and we have the natural frequency of the structure omega 0 equal to 2 pi radian per second. If we multiply the peak relative displacement by omega 0, then we have 2 pi times 5.637. We have 35.42 centimeter per second, and this is very close to the peak relative velocity, 35.05 centimeter per second. If we multiply the peak relative displacement by omega 0 square equal to 2 pi square times 5.637 equal to 222.5 centimeter per second square, then it is close to the peak absolute acceleration, 223.6 centimeter per second square. And this result is case by case, or is it always true? That's the question for all of you. And in this lecture, we have used some reference. You can find the ordinary differential equation from any textbook on engineering mathematics. You can find out the reference for difference equation from any textbook on engineering mathematics. And this is the video for lecture 1 in English and Chinese version. The video for lecture 2 in English and Chinese version. The videos for lecture 3, the video for lecture 4, video for lecture 5, video for lecture 6, and the video for lecture 7. And this is the Chinese version. This is the website for Chinese version. And the English one is the current one. It's under construction. And in this lecture, we have derived the motion equation of the structure under base excitation. And this is an ordinary differential equation. Under the assumption that the ground acceleration is constant within a sampling interval, that means that it's constant between two consecutive sampling instances, that the ground acceleration becomes a piecewise constant function. With this assumption, we can reduce the differential equation into difference equation, so that the seismic responses, including relative displacement, relative velocity, and absolute acceleration, can be solved step by step. That's all for this lecture. Thank you. See you next time. Bye-bye.